Colorado. I'm starting my talk with an acknowledgement to personally recognize the Ute, Cheyenne, and Arapaho peoples where I currently occupy. May we live in respect and with a respectful relationship with all beings and commit to working towards an understanding, justice, and reconciliation. Now today, we're going to explore one of the tools that's available at UNAVCO called the GPS Velocity Viewer. And so I'll be providing a brief overview, discuss ways that GPS can be used in the classroom and to investigate ground motion. We'll demonstrate it and let you guys have lots of hands-on experience with it. Some questions to think about is, how do we know that tectonic plates are actually moving? And what evidence do we have to answer that question? And, if the ground's moving, what's the impact, potential impact on society? So kind of stepping back, who is UNAVCO and what do we do? So I mentioned that we're a nonprofit organization. We're university governed, and we facilitate geoscience research and education using geodesy. Now, geodesy is the science of where things are, where they've been, and where they're going. And we support researchers around the country and the world to use geodesy in their science. And on the right-hand side of the screen is a kind of long list of all the different areas where where scientists have applied geodesy to their studies. Within UNAVCO, we have an education and community engagement group. And sorry, I'm starting my timers. I just wanted to move things, make sure I don't lose track of time. So we have a lot more than education resources, but I imagine a lot of you are very interested in those. So we have a number of areas that have the modules and activities, hands-on demonstrations. If you are more in a university setting, you might be interested in the technical short courses and some of the technical webinars that we put on. We also have resources for mentoring students, and I would say that's useful both for university as well as K-12 situations. And a big part of what we do now is also student internships, both for community college level students as well as students who are rising juniors and seniors, and then early graduate students. So I've been banding the word around about GPS, and in the chat, what I'd like you to do is give some examples of how you use GPS in your life, in science, or in the classroom. Go ahead, we'll take maybe a minute or so. Don't be shy. Yeah, I'm seeing a lot of, navigation, geocaching, finding a new place, Google Maps, weather balloons, that's cool. I don't know what Komoot is. You've used it in teacher professional development, mapping wetlands. Okay. GPS in our flight simulations. Yeah. And in even my spacecraft MS is the farthest object to use GPS for navigation. Yes, very cool. So thanks, yeah. So today I want to go into a little bit more depth about other ways that you can use GPS. They are used in scientific settings, as I mentioned, and a high precision permanent GPS, like what I'm showing in the bottom right here, is fairly large. Its platform is probably 2 feet across, 1.5 feet across, and then its monument legs are attached to the ground and into the ground about 10 feet. That gray dome is just to protect it from the weather and from animals, birds. But inside there is an antenna. And then there's associated equipment, such as the solar panel and stuff inside. So the thing to remember is, if the ground is moving, the GPS station moves. And I know this is exactly opposite of how most people use their GPS on their phone or in the field, is that they're walking around and finding a location or identifying a location. And in this case, with what we're doing is we're attaching it to the ground and seeing how the ground moves around. Now, basically, the way GPS works is there are satellites, over 30 satellites, well, there's about 30 satellites orbiting the Earth. A couple of those are spare. And they are constantly pinging, saying, here's my satellite number, I am located here. Here's my satellite number, I'm located here. Oh, and this is the time. And for the GPS to figure out where it is, it needs to take the answers from 4 satellites to figure out where it is. The 4th satellite is because the clocks on the GPS antennas is not as precise in the receiver on the Earth compared to the clocks up in space. Plus, you actually have to deal with relativity because these satellites are moving very, very quickly. Additionally, to kind of keep track of these satellites, there's ground control stations. So let's talk a little bit about the data. Well, so I have a diagram that shows the many different ways that GPS can be used. But thinking about this in a classroom environment, how do we often have our students jump into data? We can have them collect the data themselves. They can use data collected by others. You could analyze the data one at a time, many locations at once, all the locations at once. That's kind of a foundation of big data. And then there's many ways to visualize this data. So you might start with a table, and as you can see, you can't really read what's on this table. There's a lot of numbers, the dates on the left side. The GPS data has been split into the 3 components of 3-dimensional space. So north, east, and vertical, at least in my reference frame. And over here, I did a dirty plot, meaning I didn't spend any time trying to make it look pretty, of the data for the north versus time. This data table actually has 7,400 rows. That's a lot of data. Well, but now you want to take these graphs and turn them into something that you can put on a map to show how quickly that location is going. So, and in fact, some of our educational resources have you go through this. You could plot that up, or you could go and download the plots. You could come up with the trend, which is, how quickly the station is moving to the north, to the east or west, or vertically per year. And then you could plot it onto an XY axis for north trend and east trend. And then you could plot it on a map. But imagine now you've got over 400 stations in California. And in fact, what you're seeing are the network of the America stations, which includes what some people might be familiar with, the Plate Boundary Observatory stations, CocoNet stations from the Caribbean, and TlayLockNet from Mexico. And there's over 1,278 stations there. So this is where you've got a big data kind of issue. Like, how can you make sense of all this if you have to start from the very beginning. Well, wouldn't it be great if you could like plot this up on a map? And we did that. This is actually a poster on the left. And then we've got the velocity viewer. And one thing that I think is to recognize is that our eyes are kind of good big data analysis tools. You know, we can sort of see patterns that's going on in these maps. And in fact, we'll actually explore some of that. So let's meet the UNAVCO GPS velocity viewer. And I'm going to go to another page. Here we are. So if you have a web browser open, go ahead and put in UNAVCO velocity viewer as your search term. And it might show up with the GPS velocity viewer as the first thing, or it might put videos up at the top. But then it's often the next item down. And go ahead and click on that link. And what you'll see is something like this. So if you see this and it's just no arrows on it, go ahead and jiggle the map around. It's a feature. No, we're rewriting the background. It's not a feature. All these vectors should be showing up the first time, but they aren't. And so a little quick orientation before I let you explore a little bit. The very first top block is the GNSS data source. What really is important is that if you see the word UNAVCO, you're looking at the Network of the Americas for North America. And it gives you even more detail about the stations. If you choose any other data source, it will have that data source is from another project, and we don't have all the details, all the position time series plots and all that. But it does allow you to select from like a half a dozen, time series. Half a dozen reference frames. So here I've clicked on the list here, and let's see if I can. So I could change this to world view. And now I've changed the reference frame. One other thing that you can do is change how many markers are showing at once, because if you show all of them and you're very zoomed out, it gets really messy, particularly in California. And then the last tip is to always draw map. You got to click on draw map for it to show the map. So go ahead and explore for a couple of minutes. I just want you to choose wherever you want to go, zoom in, zoom out, change reference frames, click on the different tools. Go explore.
I put the link in the chat for you.
Hey, thanks, Carla. I was just about to do that.
Okay.
Susan, I'll answer your question in a little bit over a minute. That's a great observation. Oops. Okay, so, oops, oh, sorry, user error here. Before I dive into one more thing about reference frames, you had a few minutes just to like dive in and get lost. I'd like is someone to be brave enough to unmute themselves and just
Shelley,
ask
just
any question.
breaking in to say that we can see all of ourselves on your screen. So if you get rid of that, we could see your slide. It's right on top of your slide.
I thought that those were
That's
invisible.
better. Thank you.
Okay, but we're not getting into this content yet. That's good to know. So what'd you guys find? I see a question from Susan. Would you like to ask that question? Okay, I'll ask it. Go ahead.
So I just wondered why California had so many. Like I go over Houston, and you just see dots. Yeah,
that's an excellent question. So California has a lot of GPS stations there because earthquakes happen quite often, and scientists have been studying it and have actually put in a really dense network all along the West Coast. At first, it was for scientific study and to understand about earthquakes. Now it'll be to support the earthquake early warning system called Shake Alert. So that's an excellent question. I have a question from Elizabeth Joyner. Does this have an API? Not yet, Elizabeth, but soon. We are rewriting it in another language. I'm hoping that it will have an API. GeoMap app might, and they have the data, all of our data. What's the scale? Can anyone tell me what's the scale of the vectors? Okay, I'll give you a hint. In the lower left-hand corner is a magenta colored vector. And this is another challenge of our interface that we're working on to improve, but that is 25 millimeters. And in fact, if you scroll down on your map, I'm using a very large system, so I can see a lot of the screen, but the key or legend is down below. And so we have a scale bar there. And so as you zoom in, the vectors all resize with them. So that's a really good question. And that is something that I often kind of have teachers kind of go through so that they can remember to have their students go through this. So one thing I didn't mention is, what are you seeing on this map as far as, each one of these blue arrows is where a GPS station is housed. It's housed at the tail of the arrow. And then the length of that is how fast it's going. And the direction it's pointing is the direction that it's moving. Now, I'm going to maybe not blow your mind, but now you can see I've changed the reference, changed the frame of reference, boy. And so before I was using a whole world reference frame, meaning, I'm sitting in the middle of the world and I'm watching the plates move compared to each other. Now I'm using a North American reference frame, and it's as if I've stuck a nail into Kansas and said, the rest of the world is moving around me. I am not moving. And so I've written this up in long language so that when you guys go home, and if you want to use this, how to explain it to your students. Because reference frame is very important, because you can see things that you can't normally see if you just used one reference frame. And in fact, so here's two screenshots, the same area of the Earth. On the left, we're looking at the North America reference frame. So Kansas, we got a nail in there, it's not moving. But you can see the edge of our continent, the edge of the North American plate in the Pacific Northwest is being crunched inland. But if we change it to that IGS NNR, no net rotation, meaning you're sitting in the middle of the world, that motion is kind of covered up by the rest of the motion of all the tectonic plates. So I'd like to take the next, well, we don't quite have 10 minutes. How about 8 minutes? And I'm not going to do breakout rooms, although I could, but I didn't tell the host that I wanted to do that, so I won't make them do that. What I'd like you to do is, for folks whose first name begins with the letters A through I want you to do the very first exploration idea. Explore near your community. For those with their first name that starts with J through L, okay, M, J through M, study the West Coast of the United States or Alaska, or, I mean, I'm not going to tie you down. You could also look at the Caribbean or Chile. And then from N to Z, I'd like you to take a look around the world and just see if you can discover the different plate boundary types using GPS data. So any questions at this point before I let you go? Okay, well, I'm not seeing any questions in chat. And I'm hoping that everyone who's all their pictures are off, all their videos off, and aren't talking to me, I hope you're there. So please go ahead and yeah, explore the Velocity Viewer. If you have any questions, unmute yourself or ask a question in the chat. I'm giving you, now I'm down to like 6-7 minutes.
You have to go to a particular website you're telling, or just to explore? Like I'm in the region West Coast.
So
my
you're
start with S. My name start with S. So
okay. So yeah, choose. So you could try to find the, sorry, user error again. Try to find the Mid-Atlantic Ridge using the data. Or maybe look at the Africa or the Himalayas or Turkey. So I might.
Shelley put the link again in the chat for you. That's where you need to go.
So I'm just going to kind of step through how I would like figured out the Mid-Atlantic Ridge, but only if you want to follow along.
oh, that's great. Very beautiful.
Very beautiful. It is.
Very pretty. It's like an art class. We are on Iceland.
How did you get so many more vectors showing?
Yeah, that's what Iceland has so many on the western coast.
I'll tell you guys in a few minutes, but if you look at the data source, you can choose one of the GEM world or maybe Eurasian. Okay, and I'll give you guys like another 3 minutes and then kind of show you some examples. Yes, remember to click on the Draw Map button. Yeah. Okay, well, I'm glad you guys had a chance to explore for a few minutes. What I'd like to do is kind of walk through just a few examples, and from each one of these columns as some ideas, and then I'll wrap up with the final slides that so you can get connected to other resources. Okay, because my timekeeper is telling me I need to keep moving on. Thank you so much, timekeepers. It really is helpful. Okay, so my first example was about looking in your neighborhood. And well, my neighborhood's a little bit boring. I'm in Colorado. It's actually not moving very much, but I have some really good friends who live in Anchorage. So I'm looking in Anchorage, and I've used the North America reference frame. Again, keeping, so everything is moving relative to this area of Kansas area that's not moving at all. And you can see I've got vectors moving in different directions. Whoa, what's going on here? These are moving south, these are moving southeast, these are moving northwest. And right here, I've clicked on the station labels so I could actually look at the data. And let's look at this. So this is a time series plot. And what do you think happened right here at this time? Anyone? Ah, yeah, someone's northeast of Anchorage. So you might be familiar with what happened in 2016 near Anchorage in the region. Tamara, Pat, Luke, awesome. Yeah, earthquake. When we have an earthquake, that's a sudden movement of the earth on either side of a fault. We can actually measure that with a GPS receiver, and we can actually see how it moves and recovers, how the ground actually recovers from that motion. Okay, quick, another place. So I guess I already did Western US a little bit and Alaska. So, but let's look into Pacific Northwest. And what do you notice about the vectors really close to the coast? Well, they're pretty long, but then you get a little bit further inland, they're shorter, and then they get shorter still. What's this tiny little plate off the coast of the United States in the Pacific Northwest? And what's it doing? It's subducting. And so I've changed this to some model data. And so that Juan de Fuca is subducting under the United States, but it's not doing it smoothly. So it's sticking. And the last time they've had a super, super big earthquake, like a 9.0 size earthquake, was 300 years ago. So it's crunching that land inwards, inland. Oops, oh my. Yeah, don't do what I just did unless you have a lot of bandwidth. And then for the last one, I'm going to zoom into here. And so I'm showing all the vectors that are available. And you notice there's no GPS in Central Africa. There are a number of GPS stations that we are familiar with in this area. And so they're moving away from the Arabian Peninsula. And now if we change our reference frame, and I'll answer that question right before I finish, how do I get the small plots? Now they're moving a little bit to the east. And since I have the plate boundary showing, kind of cheating, because now we can say, oh, wow, okay, there's a rift zone here. So to answer your question, Eric, how do you pull up the small plots? Well, the data sets where you can see the plots are the North America data sets. And let's see. And you have to click on station labels. And I think I just killed my computer. Okay. While it's doing that, let me finish up the slides, and because I think I have 2 more minutes. Okay. So if folks want to put, okay, 1 minute, but don't stress. Okay, cool. Hey, in the chats, put down where you explored and what you noticed. Just one thing. And then I just wanted to let you know, I know at the beginning I talked about different teaching resources, but these are particularly useful for looking at velocity viewer. Measuring plate tectonics is a very good animation. It explains reference frames in a visual way, so I think that would be useful. How GPS measures ground motion kind of takes you from the velocity viewer to actually a hands-on demonstration. More about geodesy, great animation by NASA, and then our educational resources. And then I want to finish up with calling pilot testers. So you guys are hopefully teaching this fall, and you might be teaching either hazards or science. There are 2 modules that I've been working with Concord Consortium with. We need pilot testers to test out, kind of like, think of velocity viewer, but you can actually plot which vectors you want on the map and study about seismic hazards in California. I've posted these slides in my folder, and so these links are available in there. So thanks everyone. And I guess just as a quick wrap up, I just wanted to also say thanks for everyone putting notes down in the chat. Some people explored Alaska and Aleutians, explored Ohio. Yeah, changing to a world-based reference frame is good for Ohio. Pacific Northwest, there's a lot of, Mimi, cool to see you again. There's a lot of vectors, GPS on Mount St. Helens, and looking at the plate boundaries. Northeast, yep, the Northeast is also kind of not super exciting, but still has that potential of a big earthquake, either down and around Charleston or the New Madrid area. So thanks so much, everyone. And hopefully I can answer any questions that you have over the next couple hours, if you think of anything. I will stop sharing my screen.
Thank you so much, Shelley. And yes, if you have any direct questions for Shelley about her presentation, go ahead and ask her in the chat. But we are going to switch right over to Elizabeth Joyner from NASA. Elizabeth, are you ready to go?
Yes, I believe so. Hello, everyone. Can you
Just
hear?
as yes, Elizabeth, you sound great. Just as a reminder, folks, I put the link again to the Google Doc where Shelley is saying all my resources are, these PowerPoints are. Just for those of you who may have come in late, there's the link in the chat directly to the doc that will link you to all of these resources. Elizabeth, it's yours.
Thank you so much, Carla and Becky. And Shelley, I always learn so much from you. This is really an exciting tool that could take hours of exploration. So thank you so much. My name is Elizabeth Joyner, and I'm from NASA Langley Research Center, and I'm joined with Maria